So definite integrals are the opposite of indefinite integrals. An indefinite integral does not have bounds, so every answer ends up with a plus c, which means it's moved up or down the x-axis. When we have bounds, that's called a definite integral. So now our answers are going to be numeric. We are going to actually get a number for our answer. Instead of just ending up with plus c at the end, we're actually going to get a number, which Tyler was right, it's the area. Now we're going to have a beginning and an end, and we'll be able to find the area. But the technique is still the same. So here you go, is the definition of indefinite versus definite. Indefinite without bounds. And then definite with bounds, which represents area, exact area under the curve. So every answer will be a number. It will be a numeric value that represents the area under the curve. So here we go. This is our first opportunity to evaluate. So our first thing is to look at this and to rewrite it to the -3 power, and our bounds are from 0 to 1/2. Our first couple steps remain the same. We identify what we want to choose for our u. So our u is going to be 2x plus 1. And so the derivative is 2 equaling du dx. And so getting dx by itself will be du over 2. So now we insert another step in the process with a definite integral, and that has to do with what the bounds are. In their original form, the bounds are on the x-axis. So from where to where on the x-axis? 0 to 1/2. We are now switching to quote-unquote the u-axis. So we need to figure out from where to where on the u-axis, which is not the same as where it is on the x-axis. So all we do is take those bounds and substitute them in for x. Okay, so it will become the lower bound 2 parentheses 0 plus 1, which turns out to be 1. And then the upper bound is 2 parentheses 1/2 plus 1, which turns out to be 2. So in other words, on the x-axis, I'm going from 0 to 1/2. But on the u-axis, I'm going from 1 to 2. And so not only am I switching out the u variable, but I'm also switching my bounds. So we come here, and our bounds are now 1 to 2 instead of 0 to 1/2. And then we'll have u to the -3rd. And then our dx swaps out to be du over 2. So now everything else proceeds as usual, where we're going to pull out the constant 1/2 out to the front before we do our antiderivative. Our antiderivative is going to be u to what power? To the -2, and then I divide by -2, or multiply by -1/2, from 1 to 2 plus c. And now there is never any reason to go back to the x-axis anymore. You don't have to resubstitute back for what you chose for u. If you do, then you're going to have to go back to your other bounds also. But you don't have to. There's no need to. You're in u. You're on the u-axis. Let's stick with the u-axis. So this would become -1/4. That's the combination of the two coefficients. And then times 2 to the -2 plus c. And then minus -1/4, which changes to 1/4. Times 1 to the -2 minus c. So Tyler, here's where you were right. The plus c and the minus c cancel each other out. And I'm going to get a numerical value which stands for the area. So I have -1/4 times, and what is 2 to the negative 1/2? Is that a negative number? No. What does it mean? It's a fraction. So it's not a negative number, it's a fraction. What fraction? 1/4. Okay, and then plus the other 1/4. So that's negative 1/16. Whoops. Negative 1/16 plus 1/4, which works out to be 3/16 when you do common denominators and stuff and work it out. So the area represented here has a value of 3/16 under the original curve. So our answers are going to be numbers, not equations. Okay, that's it. That's the only new concept we have today. The only new concept is changing your bounds to match the new variable. So we're just going to practice that a couple different times. Alrighty, so we're going to rewrite this as 0 to 2x and then x squared minus 9 to the negative 1. Yeah?
Can we not leave it like the x squared minus 9 underneath?
Oh, you can.
Okay.
Yeah, you can. Some people have trouble, and so it's easier for them to see it in parentheses, and then they know what to pick. But if you knew to pick x squared minus 9, then yeah, go for it. Just go right for picking that. So x squared minus 9 will be our u. So 2x is our derivative, du dx. And so dx by itself will be the fraction du divided by 2x. And I need to convert my bounds. So my bounds are no longer going to be 0 to 2. My bounds will be 0 squared minus 9, which is negative 9. So my lower bound would be negative 9. And then 2 squared minus 9, that'll be negative 5. So my bounds are now from negative 9 to negative 5 on the u-axis instead of 0 to 2 on the x-axis. So I'm going from, now make sure you get them in the right order, negative 9 goes on the bottom, negative 5 on the top. X over, so Tyler, we can put it back and we can put u back on the bottom like that. And then du over 2 dx. So what I notice, 2x. What I notice is I can pull the half out to the front and I can reduce my x terms. So that leaves me with negative 9 to negative 5, 1 over u du, which we're really familiar with as an antiderivative now. So 1/2 bracket natural log absolute value of u going from negative 9 to negative 5. And here's where those negatives, the absolute value is important because it's going to change those negative numbers to positive numbers. So it'll be 1/2 of the natural log of the absolute value. Okay, so that's going to change to a 5. It's positive. Minus, plus c. Minus 1/2 natural log of the absolute value of positive 9 minus c. So our things simplify. And I do have 1/2 in common. So you'll probably see the answer written like this. The natural log of 5 minus the natural log of 9 with the 1/2 out front. That might be the way you see it. But you also might see it this way. 1/2 natural log of the fraction 5/9. Because subtraction and fractions are the same in natural logs. That's the property. So be aware, on an FRQ, they will accept either of those answers, the subtraction answer or the fraction answer. Either way, they're equivalent on an FRQ. But on a multiple choice, you might have to find the right one, which will probably be the fraction form. Okay? Okay? All right. Last question of the day. It's already written in parentheses for us, so we can go right away to choosing our u. So Ian, if you're choosing, what would you choose as your u? Okay, why would you choose secant squared?
Because the derivative is 10x.
Derivative of secant squared is not tan x.
Well, I would pick 10x.
Why?
Because the derivative of 10x is secant.
There we go. Okay, so we go the other way around. So yeah, we want to choose tan x as our u. The derivative is secant squared x. So then getting du alone, getting dx alone would be du over secant squared x. Do you see how these problems are designed? Okay, with intentionality. They're designed to drop out. All right, now we want to take our bounds and we want to know what tan of 0 is going to turn into, and we want to know what tan of pi fourths is going to turn into as we switch to a different axis. All right, so the tangent of 0 is 0. You should know that from your unit circle. And the tangent of pi fourths is the same thing as the sine over cosine of pi fourths, which is 1. All right, so our original problem now becomes, instead of 0 to pi fourths on the x-axis, it'll be 0 to 1 on the u-axis. U goes in for tangent. Secant squared remains the same. Du goes in for dx. And so in beautiful fashion, this will simplify to a gorgeous antiderivative. 1/2 u squared plus c from 0 to 1. And really, we can't get much easier than that. You do not need to go back to pi fourths. Just stick with the new axis and the new bounds. So sometimes I see people go back. It's not wrong to go back to 0 to pi fourths, but if you do, you're going to have to go back to tangent of x also. And it's not wrong. It's just 2 extra steps you don't have to do, and the math is usually harder. This is easier math, so when we plug in, we're at 1/2 times 1 squared plus c minus 1/2 times 0 squared minus c. And so we end up with 1/2 as the value of the area that's trapped under this curve between that and the x-axis.